So do you guys remember me saying the word optimization at any point?
Nope.
What do you think that sounds like you're doing?
Simplifying, like
Optimization, optimizing.
like
making it efficient.
Yes. So optimization is all about efficiency. We're looking for maximal or minimal products in the end.
Okay.
Like even if you look at these problems, one of them says greatest area. We want to maximize the area that we can make the fencing enclose around. Or if we're talking about business, we want to minimize the cost of our business, maximize our profits, right?
Gotcha.
So optimization is used in a lot of spaces. Calculus can be used in a lot of spaces. Sometimes it's overkill, but it will get you the most precise answer. So as far as the optimization process goes, when we are looking at optimizing a problem, we want to make sure that we're choosing variables that, fit the scenario. Most of the time I will be using X and Y, but if we're looking at volume and you want to use radius and height, that's fine. And we are going to write something called the primary function, the function that we are wanting to optimize, whether that's area, cost, whatever. Most of these are going to require a secondary function though, because if your primary function is reliant on two variables, we're going to need that secondary function to kind of get that primary function dependent on only one variable.
So you have to tie one of the two variables to the other variable.
Yes, absolutely. All right, so once you have that primary function dependent on only one variable, we want to get our interval that the primary function exists over. So basically your domain. For area, obviously, if we're looking at one of the sides of a dimension or one of the sides of whatever shape we're looking at, we want that minimal side length to be 0. Can't go beyond 0. It has to be positive. And then there's probably going to be a maximal end that you can make that side length be. Probably however long the perimeter might be. And then we're going to use our extreme value theorem process to optimize the function. So find your critical points and then compare those critical points to the endpoints of your interval. Probably going to be the critical point, but occasionally it could be the endpoint. Still worth checking. All right, example 1. A gardener wants to make a rectangular enclosure using a wall as one side and 120 meters of fencing for the other 3 sides. What dimensions produce the greatest area? What is the greatest area? What do you think we should do first before we even think about functions and variables?
Draw it.
Yes, draw a visual. Every time you do one of these, draw a visual. So let's draw a wall. Maybe it's a brick wall. And keep in mind it says rectangular enclosure. That is key. The sides are probably not equal. All right, so we have a visual. Everything except the wall is the fencing. What do you want to label these? I want to use X and Y, but
You want to use X and Y?
Yes.
Or, okay.
preferably.
So our long sides could be X
Sure.
and the short side is Y.
So reading the problem over again, what information do we know about this?
We know that we have 120 meters of fencing.
Mm-hmm.
So 2x plus y is 120.
So basically that's our perimeter, right? Now, you don't actually need to label this as perimeter. In fact, when I go into my problems, I don't actually label stuff. I just start writing my equations, optimizing it, doing all that stuff. But being that this is your notes, you're probably going to want to come back later and know where you got this information from. And labeling that does so very quickly. Now, what are we trying to optimize here?
The area.
Right, so that makes the perimeter our secondary function. Let's get this reliant on one of the variables so that we can use this with our area function later. What's the smartest variable to isolate?
Y.
Yeah, so solve for y. Y equals 120 minus 2x.
Oh, okay.
That's it. Now you guys said that we wanted to optimize the area, so let's get an area formula going. How do you find the area?
X times Y.
Yes. Now, if I want to write an area function dependent on only one of those variables, if I replace the y with that expression, what's going to go in here? Is that a of y or a of x?
A of X.
Yes. Bring down that x, replace the y with the 120 minus 2x. And we have an area function. Now, how do we find critical points?
Set the derivative equal to 0.
Set the derivative equal to 0 or
What doesn't exist?
doesn't exist. This is a polynomial, so it's going to exist everywhere. In fact, I think most of your functions, it'll probably exist, but still think about it. It's worth mentioning right now. And since I'm going to have to take the derivative, why don't we just make this look a little bit prettier and multiply the x out? And let's go ahead and optimize. Again, you do not need to label this. This is just something maybe you want to write in one of your problems. All right, what's our derivative?
120 minus 4X.
Perfect. Okay, and then you guys said set it equal to 0. Also consider where it doesn't exist, but it's going to exist everywhere. Solve for x, and what do you get?
X equals 30.
X equals 30. Anyone notice what I forgot to do?
Meters?
What?
You have to label meters.
Oh, no, not necessarily. So if I go back up to my process, and yes, I would label it in meters whenever I write my final answer up. We are starting to optimize, obviously, but we want to compare the endpoints of our interval and the critical points. We never looked at making an interval.
Okay.
So I'm going to go back to, come on, you can do it. Here we go. So I'm going to go back to our area function, and I'm going to be considering both the area function and the perimeter function to help me figure out my domain for my x. And usually after I write my area function or whatever function is my primary function, that's where I'm going to write the domain, because there could be additional restrictions that I wouldn't see when I write my perimeter. Plus, I also want to know what the variable is that I'm going to be writing my domain for. So obviously for my area, or just even for the x, what's the smallest amount of fencing that I could allocate to my x?
0.
Yeah, the 0. Now, we really wouldn't have a rectangular enclosure if it was 0, but I'm still going to consider it anyway. So I'd still have fencing, it's just.
You're just putting fence on a wall.
Just be on one side. Now, let's look back at our perimeter formula. If I cover up that y, how much fencing could I allocate to my x?
60.
Yeah, 60. I have two sides with the x. I could put 60 on one side, 60 on the other, right? Again, doesn't give me a rectangle, but I can still put the fencing there. So as far as actually doing the extreme value theorem process, we're going to set up a table and compare the areas at the endpoints of our interval and at the critical point that we just found. like I said earlier, most of the time it's probably going to be that critical point, but it's still worth looking at the endpoints. All right, so you get your calculators out, I'll get mine, and we can think about the area. So it's 120x minus 2x squared.
I think that's 0.
Hey, who would have known? I'll do 60, you guys do 30. Hey, again, who would have thought the area would be 0 if we only had the fencing allocated to 2 of the 3 sides? Anyone have the area for 30?
1,800.
That's what I got. Anyone else get that? Cool. Yay. All right. So we were looking for the greatest area, right?
Yes.
Any questions so far? Okay. So final answer. Max area. 1,800 what?
Meters squared.
Yes, meters squared. And then it asks for the dimensions. Obviously, we have 30 meters by what? What would the y value be?
Well, it says 2x plus y equals 120, so 60.
Yeah, and honestly, we can even use the formula that we saw for the y to figure that out.
Yeah.
Beautiful. How was that? Cool. Ready for the next one? Okay, flip your papers over. All right, remind me to write a little bit smaller in this.
Got it.
So it says a tank with a rectangular base and rectangular sides is open at the top. It is to be constructed so that it is, cross out 3, write 4. I printed these before I realized that I forgot to change that. So it's constructed to have a width that is 4 meters and its volume is 36 cubic meters. If building the tank costs If building the tank costs $10 per square meter for the base and $5 per square meter for the sides, what is the cost? What is the cost of the least expensive tank, and what are the dimensions? Words. What should we do first?
Let's draw it.
Yes,
draw it.
draw a picture. Try your best to draw a rectangular tank. And I'm gonna try to draw it so that the top looks like it's open. Does that look open? So we know that the width of the base is 4, but we don't know the length of the base or the height of the tank. Do you care which one we label X and which one we label Y?
No.
The height should be 1.
We can do that. That's what I did on my paper.
Wow.
Okay. So what information do we know right now?
You know that our volume is 36 cubic meters.
Yep. And how do we find the volume of the tank? Yeah, length times width times height. So that would be 4 times x times y. And what are we looking to optimize here?
The price.
Yes, the price, the cost. So that makes this our secondary equation. What variable do you want to solve for?
Let's solve for x.
Sure. All right, if I solve for x, what do I get?
X equals 36 divided by 4y.
36 divided by 4y, which reduces to 9 over y.
Yeah.
All right. Let's write our cost function. Now, just speaking in general terms, how would you calculate the cost? We know the cost of the base and we know the cost of the sides, but how do we get the overall cost of the tank? It says that the base costs $10 per square meter.
So 10 times 4y.
So 10 times the area of the base?
Yes.
Yes.
Oh, no, for the base, so 4x. Okay. Plus, side times cost.
All right, so let's write up a formula. The base you said was 4x times, what's the cost of the base? $10 per square meter? Plus our sides.
Ooh.
Go ahead.
8y or 2 times 4y for those two sides.
Ooh, yes. That is not something I noticed when I first did this. I was going too quickly. You only have the two sides that are that have an area of 4y. So that would be a plus 2 times 4y.
And then 2 times xy. Right, for the other two sides?
Yes. X, Y are the length, where is the area of the other two sides? Multiply that by 2. And then we need to multiply by their cost, which for all the sides, it's just $5 per square meter.
We can totally simplify that.
Is that okay? All right. So we decided to solve for x before. So when we plug in 9 over y into the x, what variable is my cost function going to be dependent on?
C of y.
Yep, c of y. So I want you guys to go ahead, plug in the 9 over y for the x's, and let's see if you get the same function as me. So let's see. 4 times 10 is 40. Replace the x with 9 over y. We get 40 times 9. That's 360 over y. 4 times 5 is 20 times 2 is 40. 2 times 5 is 10. I'm going to replace the x with the 9 over y, so that gets me 90. But the y in my numerator with the y in the denominator cancel out. Did you guys get that?
Yes.
That better? Okay. Now, what I forgot to do last time was to do the domain after we wrote our function, so let's go ahead and do that now. And it's a good idea, like I said before, to wait until now to do it. That way you know what variable you're going to make your cost function dependent on. All right, so let's see. Looking back at our volume function, or the volume equation right here. Pretend that the x is not there. What is the smallest, or what's the biggest value that the y would end up being?
9.
All right, and then I can technically plug 9 into my function, so I'm gonna do the equal to. What is the smallest height that we could make the volume, or make the height?
Still 0.
Yeah, 0. Is it gonna be equal to though?
No.
Why not?
Because it's the denominator.
Correct. Can't divide by 0, so we're gonna have to say this time not gonna equal 0. Not something that you might have noticed the first look. Okay, you ready to optimize? Do it. Go ahead and take the derivative. When you guys take the derivative of that first term, how are you visualizing that? To make taking the derivative
Oh, it could
easier?
be 360 y to the power of -1.
Yes. I'm gonna recommend you look at it that way to make taking the derivative that much easier. All right, whenever anyone has the derivative, go ahead and say it out loud.
Do you want the first term in fractional or in the negative exponent?
Negative exponent for now is
Okay.
fine.
Negative 360 y to the -2nd plus 40.
Everyone get that? Okay. All right, how do we find our critical points?
So they're equal to 2.
Do you want me to put that in fraction form now?
I think it looks easier to do.
In fraction, okay. Now, while I'm writing this, can we talk out loud about the other way to find critical points?
That does not exist?
Yep.
Oh,
So where would this not exist?
at 0,
Okay, at 0, but what do we need to check?
the domain.
Correct. Is 0 in our domain?
No.
So what does that tell us?
That it doesn't even matter.
Yeah, it doesn't matter. 0 doesn't matter. It's not a critical point anyway. Okay, so how do I go about solving this? Because this will get me a critical point.
So that first term has to equal -40 for it to equal 0. Yeah.
Yeah.
Equals. So. Oh, 36 divided by 9 is 4. So y squared would have to equal 9.
Let's see. So we
Or
could
big
literally just swap the position of these two. And that's kind of what you get by cross multiplying
Oh.
anyway, right?
Yeah, I didn't do that.
So if you do want to cross multiply, we technically get -40 y squared equals -360. But you'd end up dividing both sides by -40. And just like Joey said, you get y squared equals 9. Is that good so far?
Yep.
Which, when I solve that, I get
It should equal
Yeah.
positive or -3, but of course it can't be negative.
because, yeah, because of our domain. Also, can we have a negative height? I asked while laughing.
Put it upside down.
I'm
Oh,
I'm
yeah,
not
sure.
sure that-
We're talking about displacement. That's when you say, Miss Sandra, let's not get all sciencey here. You're not good at it. All right, extreme value theorem process. So I'm taking my y values, putting it into my table, and I'm going to be plugging them into what?
C of y.
C of y. All right, so what numbers am I plugging in? Obviously 3.
Yeah, and I mean 9 too.
Mm-hmm.
Are we gonna plug in anything for our left side? Because
Nope.
we can't plug in 0. So.
Can't plug in 0. So that's it. I'll
It's
go
not
ahead and
worth it.
plug in 3. Someone else plug in 9.
into C of Y.
Yes. All right, I'm getting $330. Anyone have 9,
I got 490.
490? Anyone else get 490? Cool. Now the question is, without even looking at the question, would you want your cost to be 330 or 490 to build this tank?
Probably 330.
Yeah, probably 330. I don't think I want to pay more money for a tank if I had the choice. And even if we looked at the question, it did ask for the least expensive tank. All right, so I am going to write, I'll just circle this here since I'm kind of running out of room. And then our dimensions. Obviously, I know the width and I know the height. But what's my length on the base? How do I figure that out?
We wrote an equation for that one,
We
actually.
So 9 divided by, what do we get for y? 3. So 3. X is also 3. Meters?
Yep.
So 3 meters for the length of our base, which is our x. 4 meters for the width of our base. And then 3 meters for the height. All right, good.
We forgot to tell you to write smaller, so.
This actually is much better than I did earlier. So
Oh,
I'm
okay,
glad
good.
I was able to get that all in there. Funny thing is I'm able to write it on my own paper. Just write a little bit too big on the board. All right, ready for example 3? All right, so technically we already have our secondary equation here. Y equals x squared. We have one variable dependent on the other. What do we do every single time we do one of these?
Draw it.
Yes. So I'm going to draw x squared, or the graph of x squared. And I'm going to draw the point 3, 0. And maybe that's like the closest point. I don't know.
Well, there you have it. You found it.
So we're basically, yeah, I did
It
that.
doesn't ask for the coordinates.
It does.
Okay, I guess.
So we're wanting to make this distance the smallest it possibly can be, right? So we want to minimize the distance. What is the distance formula? Anyone remember? I think this goes all the way back to the pre-calc review chapter. It's a play on the Pythagorean theorem.
Yeah, I'll leave this one for someone else.
It's like something square root in parentheses. Like, I don't know if the variable.
Wait, is it y2 minus y1 squared?
Oh.
Yeah.
cool.
I typically like to put the x first, but that's
Plus
fine.
X, yeah.
Yeah.
Minus x1 squared.
So the distance is like your hypotenuse of your triangle, and then you have the x squared plus y squared. With the square root over it, obviously, if we solve for the distance. All right, so let's write our distance formula, except look up here, we have our secondary equation. Kind of, I got rid of it. There we go. So if I look at this coordinate over here, I want to leave my x alone. If I plug x into my formula, what do I get out?
9.
This formula.
Oh. What?
If I plug x into y equals x squared,
Yeah.
what do I get out? It's
Y. You get Y.
You get x squared.
which is x squared.
Okay, okay. It was a confusing question.
Right? It sounds so ridiculous. But it's
If you plug
literally
in
just
X,
squared.
you get X.
Yeah. Plug in x, you get x squared. So instead of the y here, I'm gonna write x squared.
Ooh, that's bold.
What's the y value of my coordinate? 0. What's the x value of my coordinate?
3. Oh, this is clever.
Now, before we start simplifying this and cleaning things up in order to take the derivative, what's the domain? Is there any restriction on the x values that I could
No.
look at?
Oh, it's tricky. We have 2 different D's.
Oh. D sub D. The
it's
domain for the
3.
distance. So that should be it. Let's go ahead and, oh, you know what? You did say a positive distance, but let me take a look at the x values in a moment to kind of, See if that would work.
I think if they were like negative, they get squared. So
They do get squared.
yes, so that should be fine.
Yeah.
Because even if this second one did become negative here, yeah, you're right, with squaring it doesn't matter. Nice. I like these conversations. This is why I like actually doing this in class. Okay, so I want you guys to go ahead and multiply out the inside, combine any like terms if there are any. Let me know what you get. Is that what you guys got?
And this is still D of X.
Yes. I guess the nice thing is that we didn't really have to combine any like terms, so we didn't have to do excessive amounts of work. You guys ready to optimize? By optimize, I mean minimize.
You mean take the derivative of?
Yeah. All right, how do we take the derivative of that? What? Yeah, we could visualize that as the power of 1/2. Way to go, Miss Sandor, you just erased everything. Okay, now what?
Oh, I always want to call it the onion rule, but it's not called the onion rule.
But we know what you're talking about, the
Yes.
chain rule.
Yes.
Okay. Someone do chain rule for me, or onion rule.
Shout out to Momana. So we've got 1/2 x to the 4th. Oh yeah, the whole thing. And then to the power of -1/2.
All right, so that's the derivative of the outside.
Yeah.
Someone else want to do the derivative of the inside?
I'm not doing it.
4x to the 3rd plus 2x minus x.
Perfect. All right, now if we want to clean that up, make it look a little bit prettier, we can. Let's see. What I'm gonna do is I don't feel like writing the 1/2 in my fraction in the end.
So
So
just
I'm actually gonna multiply the 1/2 into this. Is that okay?
Oh, because they're all being multiplied by each other.
Yeah. So it would be 2x cubed plus x minus 6 all over
Wait.
that square
Wait,
root.
-3.
Yes, minus 3. I only divided 2 of them. And then you'd have that as the square root in the denominator. You can leave the power as 1/2 if you don't feel like having the square root though. All right, how do we find our critical points?
We're setting it equal to 0.
Yep, set it equal to 0. Because I'm fairly certain that that denominator would not have any x values that equal 0.
Okay.
To signify does not exist. All right, so if I set this equal to 0, what do I really end up looking at?
The numerator.
The numerator, yeah. Because we'd multiply both sides by the denominator and, you know, bye-bye. Any ideas? Should I take the silence as, yeah, I don't know what to do.
Yeah, take that.
I'm looking at this and I'm thinking it's probably not going to be easily factorable. Because what I would like to do is take an x out of each term, but I don't have an extra x to give. And then we don't have a cubic formula that we could use to get rid of the, or to actually solve this, unlike the quadratic formula. That would be super nice, but we don't have a cubic one.
When you set 2x to the third plus x equal to 3,
Nope, don't do that.
Okay, I'm not going to do that then. But
You can't add 3 to the other side and then factor out next.
Nope.
And then set it equal to 3.
That's not a kosher rule.
Don't
do that.
Okay, well, that was my idea, so I'm out of ideas.
That's my only idea.
I'm going to allow us to use the calculator to solve this.
Because x should equal 1, right?
Yeah.
Because that's what happens when you set it equal to 3.
You
then.
just did guess and check, right?
Yeah.
Well, I mean, a knowledgeable guess and check. I'm going to write a little note here that I want you to write on your paper. So it's not factorable, or at least not easily factorable. No, it's not factorable because one of the solutions would be imaginary. We do not have a cubic formula. So annoying in the video.
You might want to close the door and people are going to go into the home.
I'm not allowed to.
Oh, really?
So we are going to use our graphing calculator to find the zeros.
But if you did set it equal to 3,
No,
but if
No.
you did, then you could solve for x equals 1.
you would end up getting an incorrect solution. You get x equals 3 because you'd factor out that x, right?
Yeah.
Which is not an actual solution to this. Yeah, don't do it. I'm not going to get rid of the derivative thing just because those are going to be useful in the future, but they're just turned off. So let's go ahead and type in 2x cubed plus x minus 3. And I'm going to just make sure that I'm looking at my standard screen because I know I've been messing with my window. Anyone have any idea on how we find the zeros? I mean, obviously it looks like it's going through 1, but what if it's 0.99?
Second trace.
Go to the left of the root. I think that looks like it's roughly in the left of it, right? Plus you see that little arrow pop up. I know I'm to the left of it. Go to the right of it. Whoop, too far. Where did I go? Okay, there we go. That's definitely to the right of my root. And it says guess. Close enough. And it is x equals 1. Sound good?
I apologize for my.
No, you are good. I have a few students that won't stop doing it. And this is like, that was actually a good opportunity to say, hey, stop. All right. How is this? Oh, we're not done.
What?
What did the
Oh, we
question
have
say?
to find a line on the point. or the point of the line.
Yes, the point on the curve.
We gotta plug it in.
Yep, find that y value. So let's go back up to our function. Plug 1 in for x.
Thanks to our observation at the beginning, x becomes x squared.
Yep.
So
So
Our-
y equals 1.
point is 1, comma 1.
And now we are done.